So we will continue with our pursuit of the topological dynamics of cellular automata. So last time we already discussed how can we introduce the topology on the space of configurations of cellular automata. And today we will essentially study the global rule of a CA and its dynamical properties, starting with some very basic ones, like when is the global rule injective or surjective. And we will establish some classical results from this theory, including the Garden of Eden theorem, which essentially says that a CA is surjective if and only if it satisfies some weaker form of injectivity. And next time we will also talk about some basic notions regarding to sensitivity to initial configurations and how it can lead to some classifications of CA dynamics. So yeah, you basically know almost all you need to know about the topology. Maybe last time we ended with an example. So let's fix some CA configuration space S to the Z to the D. So let D be a subset of Z to the D finite, and let C be some configuration. We define the cylinder set which we will just denote SYLCD to contain exactly all configurations which agree on the domain D. So it should be an easy observation that each open ball is a cylinder. It just suffices to take as D the box of some fixed radius. Yeah, and then CD is BRC. So that can be our first observation. Our second observation is that every cylinder set is both open and closed. In the topology, and this is an exercise in case you don't see it immediately. And essentially the family of all cylinder sets, as it contains all the open balls, forms an alternative basis for this topology. And in some sense, we will see that it's more natural. So maybe let's just, to get used to this metric space more, let's quickly talk about continuity. So a map F, or like a self-map F, is continuous if for all epsilon and for all C there exists a delta such that if the distance of a configuration from C is less than delta, then the image distance is less than epsilon. So this is a standard definition. And in particular, for epsilon being 2 to the minus 1 and some c, continuity implies the existence of some R, we can say natural, such that the value of C at 0 is completely determined just by the finite region given by the box with radius R, or the ball of radius R. Yeah, so is completely determined by the finite region C restricted to this box. Yeah, that is because for this epsilon, we literally just want the value at the origin to be equal. So, and then we can find some delta such that if any two configurations essentially agree here, then they will agree at this value. So now the whole point is that this R now depends on C, and we will discuss that it actually does not need to, because every CA map is here, yeah. If this is uniformly continuous, for instance. And the second thing we can briefly discuss is how convergence looks like. So let yeah, they're doing the maintenance of the building. Be oh no. I don't know if my post-production skills are enough to make the recording. Okay, well. So it converges to some C if and only if for every finite D, the sequence restricted to D eventually stabilizes exactly to this. So this is essentially a very simple observation. You can also think about it at the exercises if it's not obvious. But from this, it is not difficult to show that every sequence has a converging subsequence. And thus that we have a compact metric space. So an alternative way to see this immediately that I already discussed last time so an alternative way to obtain the exact same topology is to consider the discrete topology on the finite set S. And take the corresponding product topology on S to the Z to the D. And you will actually obtain a topology with the basis being exactly the cylinder sets. And since it's clearly the case that S is compact from Tikhonov's theorem, we immediately get that any product topology of a compact space is also compact. So we get that S to the Z to the D has a compact topology. Or is compact. Yeah. Are there any questions?
One question. What you wrote in the very beginning, the cylinder of C and D is equal to PR of C. Is that index R correct?
I'm saying if you take D to be this, then the cylinder is exactly the set of configurations that agree on this region around the origin, which should be exactly like the ball with radius 2 to the minus r, which is exactly that you agree on the.
Yes, okay, but okay, I'm used to other notation then.
Yeah, right. It's maybe a bit non-standard, but we did discuss that BRC denotes a ball with radius 2 to the minus r, essentially. Yeah. So, is a ball with radius. Yeah, thanks for the question. Okay. So my aim is not to give you an overview of compact spaces. Hopefully you have some experience with them from other classes. But in case you don't, I'll just list 3 properties that we will use in this lecture. And I refer to some textbooks in the notes that you can look into if you want to understand in depth why they hold. So let XD be a compact metric space. The following holds. So first, if f from x to x is continuous, then it is uniformly continuous. The second point is that let K1 superset of K2 be a sequence of non-empty closed sets okay, now we're in X. Then their intersection is non-empty. And the last property we will use is that any continuous map, which is a bijection, is a homeomorphism. So if f from x to x is a continuous bijection, then the inverse is also continuous. Wonderful. So now we're ready to prove one of the first fundamental results about cellular automata. So the Curtis-Hedlund-Lyndon theorem so let F be a self-map of some configuration space. Then F is the global map of some cellular automaton if and only if F is continuous and commutes with every shift map. So it's actually pretty straightforward. I will let you finish writing this. So one implication is a straightforward verification, and the other one uses compactness. Can you guess which one is the straightforward one? Sorry? Yes. So let's start with the easy stuff. So let F be the global map of some CA. With radius R and local rule F. So we essentially already discussed that it commutes with all shifts. So I will not even, so we already know. F commutes with all shifts. So we will verify continuity. Its continuity. And that should be relatively straightforward. So yeah, so let epsilon be 2 to the minus n for some n. And let C be some configuration. So we put delta just to be 2 to the minus n minus r. And that's it. So let C prime be such that C prime on this box agrees with C. Then we verify that FC agrees, okay, FC prime, so it's symmetrical, agrees with FC, yeah, on this area. And that's relatively, yeah, that's pretty straightforward. Do you see it, or would you like me to write it down explicitly? Who would like me to write it down? Okay. Yeah, so let V be a vector whose norm is at most R. We will look at Fc prime at position V. By definition, this is just the local rule applied to C V plus N1, C V plus Nk, where, yeah, N1 up to Nk is some enumeration, is the neighborhood, yeah, of the neighborhood. So the neighborhood is this, right? Is an enumeration, okay. That's the neighborhood. And now, since each Ni has a norm, we should have, you should have said something. There should, but this is easily correctable. There should be n's, right? And we should take this vector with norm smaller than n, or equal to n. Now this vector has a norm smaller or equal to r, so the norm of v plus ni is less or equal to norm of v plus norm of ni, which is less or equal to n plus r. So it just means that each of these vectors belongs to this box where the two configurations agree. So. and there should be prime. Great. It was already a spoiler because it does not matter. So this star is exactly the same if we replace the values of the local rule with the values of C. And that's just f of C at position V. So they really agree where they should. All good? Great. So the opposite, or the implication, is not much harder actually. So let f be continuous. Then, since we have a compact metric space, f is uniformly continuous. So pick okay, let's make this not such a long blackboard row. So let's pick some epsilon, let's say the largest possible. Then there exists some R in N such that for all configurations, let's say C prime, if C and C prime agree on this region around the origin, then their images will agree at the origin. This is the epsilon equals to 2 to the minus 1. And that's somehow it. This is already a clue. This will be the radius of the CA. So fix R to be smallest such R. We define the local rule F to be exactly F of some configuration C just at the origin for any satisfying that, yeah, C yeah, again, where is the neighborhood. Yeah, so essentially now we have that the value of every configuration at the origin is determined by this finite region. So we just define the local rule to map that finite region onto the image. And now in order to verify that this is really a local rule of a CA with radius r, we have to verify that this holds not only for the origin but for an arbitrary position, right? So let V be an arbitrary vector. We want to show that. Yeah, and let C be an arbitrary configuration. We want to show that the image of the global map of C at position V is exactly the local rule applied to what it should according to the CA definition. So for this, we can notice that Fc of, so we have to use somewhere the fact that F commutes with the shifts, and this is where this will now be used. So this is the same as F of sigma V applied to C, or, okay. It's the same as sigma V of Fc at position 0. This is just the definition of the shift map. And now we use the commutativity of these two operators. So that's like F of sigma V of C at position 0. Here we can use that at the origin. We already know that we have this local rule. So that's essentially exactly F of the configuration sigma VC at position N1, sigma VC at position Nk. And now we again use the definition of the shift map. So this is the same as C at position V plus N1 all the way to C V plus Nk. And I get to write a square. Great. So that's nice because now we know that indeed this topology is a natural topology under which the global maps of cellular automata behave nicely. They're continuous, they're uniformly continuous, and they commute with shifts. And we have a characterization. Yes?
How do we guess the K? Are we just taking K to be...
So K is 2r plus 1 to the d. It is really just an enumeration of the neighborhood of a CA with radius r. So the neighborhood viewed as a set is just this. But if we want to really apply the local rule to a configuration, we have to just enumerate the elements of the neighborhood in some order. So this is where I just write it like this, but hopefully it's clear. It's just some enumeration of this set. Yeah. Great. So we have enough time for me to show you the first application of the Curtis-Hedlund-Lyndon theorem for so-called reversible cellular automata. Those are a pretty interesting subclass of cellular automata to study because their dynamics is reversible. So in some sense, they model some nice local properties of some physical worlds. So let's start with a definition. We say SCA the to the d f is bijective if f is bijective. That's pretty what you would expect. We say A is reversible if it is bijective, and the inverse is again a cellular automaton. So we just want to be able to simulate both the forward and the backward dynamics by a CA. Is the global rule of some CA. So, proposition. And the proposition is that a cellular automaton is bijective if and only if it is reversible. So the reversibility is not any extra condition, actually. SCAA. If and only if it is reversible. So one implication is not worth mentioning, but let's assume that A is bijective and we want to show it is reversible. So thanks to the Curtis-Hedlund-Lyndon theorem, so due to the Curtis-Hedlund-Lyndon theorem, it suffices to check what? To check that f to the minus first is continuous and commutes with all shifts. So it is continuous because we are again in a compact metric space. So it's due to, I guess, 0.3. And so let's verify that it commutes with shifts. So let V be some vector used for the shifts. So and let C be some arbitrary configuration. So sigma V of C is something like what do I want to do? Maybe so let's just figure out how we could come up with this. So we know that F commutes with the shifts. Right. Right, so it would be nice to take so maybe we can try to take C to be the pre-image of C. So we know because F is a bijection, and we know that F commutes with this. So this is just sigma F of C, and this is F sigma V of to the minus first of C. And now we just apply, F inverse to both sides. So, and we get F to the minus first sigma V C is sigma V F to the minus first C. Yeah, I guess there's many ways to show this. And in the second lecture, we will examine more properties related to reversibility, surjectivity, and injectivity, but now we can take a break.